the union of events. If E and F are events, what is the probability that E or F occurs? The word or here is indicating that we want the probability of the union of these things, or the overlap. So we draw the symbol that looks sort of like a U, we just never put a tail on the end of it. If we simply add the number of elements in just E to the number of elements in F, the problem is we'd be including any overlap. So that's why we really want to make sure we're not using the overlap twice, right? So if things are in E and in F, we don't want to count that event more than once. It doesn't, it messes with our probability. So we don't want to count the same thing twice here. So in order to kind of account for that, what we're going to remove is the intersection. We're going to add everything in E to everything in F, but then we're going to take away one of the overlap. And that's because that'll leave behind the overlap for one of them. So what I mean is for, let's say we have, I don't know, let's just make something up with like some letters here. So in the first one, let's say we have the letters A, B, C, and D, and then the other one we have D, E, F, and G. And if I wanted to just do the ones in the circle on the left, that would be A, B, C, and D. If I also wanted to include the ones from the circle on the right, that would be D, E, F, and G. The problem is I don't want to include this letter D twice when I'm just saying all of my options. So what I'm going to do is say, okay, the overlap is D. I'm going to take one of those away, and now I'm not repeating. We're not kind of counting that overlap twice. All right, so what is the probability that a card is drawn at random from a standard deck of 52, that it's either a face card, like a king, a queen, or a jack, or it's a spade? And remember, a spade is one of the suits. So for our king, queen, and jack, we can have those in hearts, diamonds, that's a terrible clubs, and we can have them in spades. So that means in reality there are 12 different face cards that we can get in the deck. So for face cards, there are 12 of these. Spades, there are 13 of those in the deck. But if we want either of those things to happen, we want to make sure that we're not counting the same thing twice here, right? There are some spades that are face cards, so we don't want to include them twice. So let's let E be face card, the event that the card is a face card, and let's let F be a spade. Okay. All right. So like I said, we want to make sure that we're not using this overlap twice. So let's find the probability of getting a face card, and that is there's 12 of them, so that's 12 out of 52 cards. And the probability of getting a spade, there are 13 spades in the deck. That's really just a fourth of the cards. All right, well, the intersection, we want to know how many cards are both a face card and a spade. So probability of E intersection of F. All right, well, that are spades and a face card, there's going to be 3 of those out of 52. So now what we want to do in order to find the probability or the union here is that I want to take I want to make sure I am taking these 2 probabilities and adding them together. And then I want to subtract off that last one. So the probability of E union F is going to be 12 over 52 plus 13 over 52 minus the overlap. So that's going to give us 22 over 52, which will simplify to 11 over 26, which you can make a decimal as well, but we could do our probability as a fraction. There's nothing wrong with that. Now, we can also have events that are considered to be mutually exclusive, and what that means is that they have no outcome in common. There's no overlap whatsoever. All right, well, if there's no overlap, there's nothing to subtract. So really, all we're doing here, even though we're technically subtracting the intersection is 0. There is no intersection. so we don't have to worry about it. So with our cards, for example, we could say that a card is an ace or a card is a queen. Well, it can't be both of those things at the same time, so we call that mutually exclusive. So their intersection is 0. There is no intersection, so we don't have to subtract anything because we're not worried about an overlap here. There is none. So a card is drawn at random from a deck of 52. Okay, so we're back to cards here. What is the probability that the card is either a 7 or a face card? All right, well, for our 7s, we can have a 7 of hearts, we can have a 7 of diamonds, we can have a 7 of clubs, or we can have a 7 of spades. Oops, that doesn't quite look like a spade. All right, for our face card, remember we can have king, queen, or jack, but for each of those suits. Okay. So we can have those for hearts, for diamonds, that's terrible diamonds, for clubs, and for spades. Okay. So we can have all of those. We want to know the probability of getting one or the other. Well, let's say that the probability of, or let's call event E, getting a 7. Let's say F is a face card. So the probability, these are mutually exclusive. So the probability of E is going to be, there's 4 out of 52. The probability of F, there are, let's see, 3, 6, 9, 12 out of 52. So the probability of one or the other happening is just adding them together. We would be subtracting 0, so we don't have to do anything special here. That's 16 out of 52, or that's going to be, let's see, 4 out of 13. The intersection of independent events. Well, when the occurrence of one event does not affect the probability of another event, we say that these events are independent. So, for instance, if we have a balanced coin toss, the probability of getting heads on the first toss is 50%, right? But it's also 50% on getting heads on the second toss. They don't really affect the other one. If I flip again, it really, every time I flip, I have 50-50 shot of getting either one. It doesn't matter what I flipped before. It doesn't change anything. So that's what independent events are. They don't affect each other. So if E and F are independent, in order to find the overlap or both of them happening, this would be sort of what we consider to be and. Then we just multiply those probabilities together. And we kind of saw that a little bit earlier when we were talking about probability. So a jar that contains 5 red marbles and 4 black ones, we wanted to know that a ball is going to be drawn from the jar and then replaced. So every time we're starting with the same, 9 in total. Okay? Then we're going to pick again. So every time there are 9 to pick from. So what's the probability that both are red? All right, well, the probability of getting red the first time, there are 5 red and 9 in total. The probability of getting red the second time, well, again, that's 5 out of 9 because we put all of them back. So we started with the same amount. So the probability of getting red and then getting red again is going to be 5 out of 9 times 5 out of 9, or 25 out of 81. And you could turn it into a decimal or percent. It doesn't matter. That would be about like 0.31, I believe. All right, what's the probability that a class of 35 students has at least 2 of them having the same birthday? All right, well, we can think of it like this. We have, we can assume that these birthdays are independent. Let's not worry about twins or anything like that. We're going to ignore February 29th. We don't have to worry about leap year. We're just talking about in general. So let's let E be the event that 2 students have the same birthday. Okay. So E is equal to students having the same birthday, or 2 students have same birthday. Okay. So the next thing we want to do is to start to think about all of the different options here. So we can consider how about the complement? That might be a little bit easier to figure out. What would be the opposite of this happening? Because we could have two students having the same birthday. We could have 3 students. We could have 4 students. We could have 5 students. I mean, technically, we could have every student. That's highly unlikely. So if we found the complement where everyone had a different birthday, we could subtract that from the probability, or from 100%, and then figure it out. So if we let the complement be what we're looking at, we're talking about no students share a birthday. And that's going to be a little bit easier to calculate. All right, so let's say the probability that nobody is sharing a birthday, and we have 35 students in total. All right, well, we have, for the first birthday, that person could have, well, their birthday could be anything, right? So 365 out of 365. All right, times the probability of having a different birthday, there's 364 out of 365. The next one having a different birthday, there's 363 different ways that they could have a different birthday. And we can keep doing this until, let's see, we want to make sure we've done 35 of them. So that's going to put us at, let's see, 331, I believe, out of 365. Okay. All right. So if we were to multiply all of these together, and definitely going to want to use a calculator for this, but we're going to do this so that there are 35 of these written out. We're going to save us some time. We're going to get about 0.186. Now that's the complement's probability. So if I want the probability of people sharing, then it would be 1 minus 0.186. That's going to give us about 0.814. That means there's an 81.4% chance of at least 2 people in the class sharing a birthday.